What's up, everybody? So welcome to geology, of course. I asked my lab students this. Let's see what we think. Here's a photo of my son and I back in our woods where I live, southwest of Oswego, cutting down a tree. It had already started to fall anyway, so we took advantage of it falling. We took it the rest of the way down, chopped it up into pieces, and brought it down to dry, where we'll eventually bring it inside to a fireplace, which we use for heat in the winter to heat the house, like an insert. What I asked them was to think about the difference between that and burning coal for heat. If I just directly did that, which happens, some people have coal stoves. There's some very major differences, but there's some very major similarities too. And that's going to be understanding those is going to be a key to unlocking what the carbon cycle is all about, how carbon is cycled through our planets through time. So let's take those scenarios. I'm just going to draw them here. I don't think that there's necessarily anything you would need to do. I could put these notes up. If somebody wants them, email me. So I'm going to draw, if you can't tell what this is somehow, let's say these are my woods. So here's a tree. All right. Now, if this falls over, let's say it falls over, and either it rots where it sits, or again, I come by and I burn it. What has happened is that through time, the sun, which is further away than this, we're just doing this as a diagram, right, has had insolation flying at our planets, and green plants have figured out the trick of photosynthesis, of taking that and turning it into essentially food, right? There's some chemistry that we're not going to necessarily get into, but is, I suppose, kind of important for this. That allows that plant to grow. Photosynthesis takes in CO2. If you've ever heard this, we breathe in oxygen and let out CO2 as a waste product. Photosynthesis does the opposite. It takes CO2 out of the atmosphere, and as a waste product, oxygen comes out. Its waste product is what we consider vital for life, right? Part of that process, and along with building the sugars, carbohydrates, whatever it is, we'll have to ask a chemist or a biologist about that. It builds the tissue of the tree, right? Which is high in carbon. It's made of carbon, right? It makes these bonds that are breakable in a fire chemically that produce heat. We're simplifying a little bit here, but we're going to get to the point. So this tree then is built out of that carbon. Now, if we knock it over and it rots, or if we knock it over and I cut it into pieces and I set it on fire, either way, you're going to let that CO2 back out into the atmosphere when that happens. The trick is, actually, let's do this first. Let's say in a different scenario, a tree, and I've got areas like this on my property, but none of us are going to live long enough to have this work. If we have a scenario where a tree falls into an area where it's isolated away from the atmosphere and it can die in a fairly specific way, like a bog, you get a boggy area, this will work. It doesn't break down and let its CO2 back in the atmosphere. Rather, it gets preserved. And if this happens on massive scales, this isn't happening in my backyard on massive scales, but if this happens on really large areas for very long periods of time, you can build up and build up and build up this plant material. But let's think about that. When that happened, right? If this happened today in Sterling, New York, yes, that CO2 was taken out of the atmosphere. That carbon built the tissue of that tree, then it fell, and now that CO2 is sequestered away. So let's jump back into the atmosphere back in the Paleozoic, when there were massive forests that today are what we have been digging up as coal deposits. They did the same exact thing. They took carbon dioxide out of the atmosphere. They built the tissue of plants and trees. They fell over into swampy areas, got preserved underneath layers of, progressively more plants and underneath other sediments, and eventually went through that process that we talked about back in rocks of like peat and lignite and different forms of coal. The trick is that carbon dioxide was taken out of the atmosphere in the Paleozoic and then sequestered, locked away. out of the cycle. If we see this as a cycle, the tree grows, gets knocked over, dies, CO2 back to the atmosphere, it's carbon neutral. The only way that this isn't carbon neutral for us being my family, is that the little lawn tractor I have here to transport it in and out, and I suppose the chainsaw burns some gas, right? Minus that, if I did this with a saw, not going to happen, like a handsaw and an axe, and then carried it back to my house, it would be carbon neutral, because the carbon it took to build this is then, when I set it on fire, comes back out my chimney and goes back to the atmosphere. Came out of the atmosphere, built that tree for a couple of decades, back to the atmosphere. That is the cycle, right? That can happen over and over again. So I do heat my house reasonably carbon neutral. Yes, I do burn some fuel to transport those trees around a little bit. Whereas if you were to just burn some coal, which maybe you do indirectly by using energy that comes from a coal plant, you're letting carbon dioxide back out into the atmosphere still, but you're letting out carbon dioxide that was in the atmosphere in the Paleozoic, hundreds of millions of years ago, that has since been sequestered in the ground and is now free to escape out back in. So what that means is, not only do we have the present day carbon dioxide around and around and around and around on this, but we're going and finding basically all, it's a weird way to think about it, but basically all of the old atmospheres we can find, we're finding all of the carbon dioxide that was in all of those too. And when we burn that coal, we're also adding that in to the atmosphere. So in a simplified sense, just thinking about burning a tree versus burning coal, see how they're similar? Photosynthesis built both of those. Both of those took carbon dioxide out of the atmosphere, and both of those released their carbon dioxide when burned. The giant difference is that this cycle all happens over the course of human lifespans and is neutral in the course of human lifespans. This process took hundreds of millions of years to preserve and concentrate that coal. And now we're getting that carbon dioxide also and setting it back free into the atmosphere. So what's the net result? Well, we have an atmosphere with more and more and more carbon dioxide in it. Like I said, we're logistically, we're breaking this unit down into just a week this time. So all I'm going to have you do is 18.4. One paragraph, two paragraphs. Check that out real quick. The rest of 18 has some cool stuff. Also has some very specific Canadian stuff that that definitely not worry. We're not going to worry about any of it. We're going to worry about these two. Check out a couple other sections if you want to, but that's it for the state of building fossil fuels and where that leads into the carbon cycle and human history. Lost my page. Give me one sec. As it turns out, carbon dioxide is very, very good as what's called a greenhouse gas. It's a really effective greenhouse gas. There's others that are more effective too, like methane. Water itself, pretty effective. And what that means is that, and this is, if you ever hear controversies, as far-fetched as they may seem to a person in my position, if you hear controversies about climate change and global warming, again, I think they're all far-fetched, right? But what things are certainly far-fetched? What things can we say are, this is just how it works? This isn't anything that's controversial at all. So here's just how this works. Let's say that here's the Earth. And here's, this whole thing will be our atmosphere, and then up in space up here, right? So the sun, again, which is much further away than this, but we're doing what we can today, sends energy towards our planet, and a lot of that energy at this wavelength, which I'm doing a terrible job at drawing, manages to make it right through the atmosphere, hits our planet, and our planet heats up in response. And then while anything that's warm gives off heat energy too. So as it heats up, it gives off more and more energy. It radiates it back out. This is like absorbing energy and radiating back out. The giant difference is that the energy that makes it from the sun through the atmosphere to hit our planet has a shorter wavelength. Anything that's warm, me right now, if you had the right kind of camera, you could pick it up. I'm giving off heat into this room by process of, digestion, the food that I've eaten and my metabolism. The planet also gives off heat, but when anything gives off heat like this, it does it at a longer wavelength. It gives off infrared radiation. Now, I'm using a touchpad here rather than my usual mouse. I apologize. These are supposed to be shorter, and then these are supposed to be longer wavelengths over here. And that longer wavelength, we can label it quick. Infrared. So infrared radiation is what's given off by everything that's warm. So this planet that heats up in the sun during the day gets warm, gives off infrared radiation. The non-debatable trick to the greenhouse effect is that CO2 and other greenhouse gases, through this diagram, which may look a little intimidating and confusing, are good, basically, if you wanted to get the short and easy version, are good at absorbing that infrared radiation. Now, this isn't like, think of reflection differently. I mentioned in the last video, like a white snow cap, or if you just throw a mirror into your front yard for some reason, that's going to allow the sunlight to hit, bounce right back off, pass right back through the atmosphere. This case is different. This is the energy comes through, warms up the planet, that planet being warmer, then gives off infrared. And greenhouse gases are good at holding that infrared energy in. You've noticed this your whole life. If you've ever left a car in a parking lot somewhere and gone to wherever you're going and done something and come back out and experienced it being hot in the car. The sunlight has no problem getting through the glass of your windshield and side windows and rear window, right? Easy peasy. Then what's it do? If it hits something shiny like a seatbelt, it hits that and it reflects right back out the window, just as easy as it came in. But what else happens is that it hits the seats and the dash, and anything that's dark colored in there that's efficient at absorbing that energy, that stuff warms up. And when that stuff warms up, it gives off more infrared energy. And like greenhouse gases, the glass in your car does not let that infrared energy out as easily. Therefore, you go get in the car after it's sat there for a bit, and it's hotter. That's all very easily observable with what's going on the planets. The arguments that are made against it are primarily people that are economically interested in not changing any of these behaviors that we have. And I'm not saying, I'm a saint on this. I have a long commute to work, which I use a gas-burning car for. You saw me with a lawn tractor and a chainsaw, right? I'm not asking people to revert back to the Stone Ages, but I am asking us to be aware of it and to, as we continue to develop technologies and come up with better ideas, that we approach those ideas from a position of knowing what we're talking about. And that is that, for certain, non-debatably, carbon dioxide is a greenhouse gas. Non-debatably, we've added more and more and more of that to the atmosphere. Therefore, there are more greenhouse gases, and the planet is warming up. Observably happening, universally agreed upon by people in the field. Very thorough reports out indicating all of it. And one of the things we've got to consider with our spiking population, which the Industrial Revolution both allowed, but is also building us towards a situation where we gotta start to wrap our heads around how to deal with this. What do you think? Carbon cycle? Ooh, there's a nice. Sorry, I didn't make it this far in the book the first time. There's a nice infographic for it. Somehow they did a neater job with their graphics than me. Hard to believe. All right, that'll be it. Again, and if I didn't mention it, when I build the test, I'm going to try to build it really off just what I said on this. So it will be a shorter one than usual because it's only a 1 week thing. So give chapter 16 a good look. Oh, that one's very cool too. And I'll try to keep the quiz pretty straightforward and short, and give us a chance to catch back up in this in this semester, and get out of here successfully. Thanks, everybody. Look for the quiz Thursday, Friday.